Sprint cars are a form of American auto racing. They race on short tracks, both asphalt and dirt. Their signature feature are their wings of massive size and angle of attack. And you can see just on that main wing here, this main wing is a square of aluminum of 5 feet by 5 feet. Massive. And you can see just by the scale of the driver's head how big the wing is and how small the car as a whole is. And because the cars are so small and lightweight with such narrow wheelbases, rollovers can happen a lot more frequently when they crash. Another cool thing about them is they essentially drift around every corner. That's because, especially on dirt, maximum traction in the tires, it's achieved at a high slip angle. The chassis' unique shape and loading scenarios will be interesting to visualize. It must be strong enough to support the forces of acceleration and downforce, and most importantly, it has to be safe for the driver and protect the driver in those rollover crashes. So to test the chassis out in the loading scenarios, there are 5 load cases I came up with. The first 2 are just steady forward motion. First one is 60 miles per hour. Second one is 120 miles per hour. And we'll get to see the different effects of the aerodynamic downforce and drag that produced by the wings. In case 3, we're going to be going through a turn at 90 miles per hour, which is pretty typical, at a slip angle of 15 degrees. And the g-force is experienced. It's just going to be 0.82 g's to the right and 0.22 g's behind. Case 4 and 5, those are crash scenarios. So that's the worst case scenario of a rollover happening. Suppose the car just hits a rut in the dirt or something, and it flies up and comes to the ground upside down, hitting the chassis in the top nodes 8 and 21. In case 5, supposing there's just a fire or something that heats up the elements surrounding the engine, and then seeing what happens with those thermal strains. And we can see here the layout of the chassis structure. The geometry was simplified a little bit. As you can see from the original pictures, the chassis is a little bit more complicated than what I've modeled, but this is it's a fairly accurate simplification. The dimensions were based on real-life short track rules, based on the rules of the Selinsgrove Speedway for the 2020 season. The rules indicated 4130 steel, which are where I got the material properties from, and I also assumed that both wings were trimmed to 25 degrees, just the angle of attack of the wings, which is pretty common. Assumptions for the loads: g-forces act on the engine, the driver, the top wing, and the front wing. So those are just the 4 elements in this theoretical car that are going to have mass. And yeah, that just assumes that I'm assuming that the chassis does not have significant mass, and I'm not taking into account other aspects of the car, such as the drivetrain or the axles or tires. The aerodynamic forces will be calculated from coefficients gathered from this study, which gives the aerodynamic coefficients at various angles of attacks and velocities and side slip angles. And finally, I'm just indicating that the g-forces and aerodynamic forces that are occurring on the engine, driver, top wing, and front wing, those are going to be transmitted to the chassis at the points where they are connected to the chassis. So you can see here's the layout of all that. So the top wing is, for example, mounted on this node, this node, this node, and this node. And therefore, the forces that the top wing experience are going to be transmitted to the chassis through those nodes, and so on and so forth for the, and that was the front wing. For the top wing is here, and again, front wing is here. And then the engine and the driver, the engine is mounted at the bottom here, and the driver, the driver's seat and the seat belt holding the driver in, those will ultimately connect here. I'm also assuming that nodes 3, 5, 16, and 18 are constrained against displacement in X, Y, and Z. And all these aerodynamic and G forces were calculated in a separate Mathematica script, which I've attached. And the actual simulations are available in the template code, which is also attached. To derive the magnitudes of the forces on the nodes, it's just I go into more detail in this document, which I've also attached. And the basic premise is just drawing a free body diagram and solving the equations to get the reaction forces. I've made some assumptions with these calculations. I've assumed that if you take a look at the sort of rectangle connecting the nodes, for example, this is where the engine connects, right here, 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 here. And if you look at this rectangle, I just assumed that the center of gravity, I assumed that it just acts kind of in the middle of the rectangle at some unspecified height. Same thing for all the other masses, such as the driver, the top wing, and the front wing. The top wing and the front wing are actually mounted at an angle of attack, and so for those, I just also assumed that the center of mass was also in between the nodes in the y direction this time, in addition to the x and z direction. The full results are available in these files. They, of course, would not fit in a PowerPoint slide even if I wanted to, but I have included the maximum displacement forces and stresses, and just some comments on each of them and some highlighted diagrams. So for the first load scenario of forward motion 60 miles per hour, we can just see the main effects, no g-forces. The main effects are just the aerodynamic drag and aerodynamic downforce. And of course, we see some downward deflection where the top wing is here. There's actually a little bit of upward deflection in the rear of the car. And even though the top wing is mounted here, that's just indicating that this deflection is having kind of ripple effects throughout the chassis, interacting throughout all the members in the middle here. It somehow leads to this one deflecting upwards. The top, pardon me, I keep mixing them up. The front wing has a little bit of deflection, not as much as the top wing. And some of that may even be because of this displacement pushing elements downwards and then pulling these elements towards it as it gets pushed downwards. Maximum displacement is extremely small, which is to be expected. Nothing crazy is happening to the chassis right now. Maximum displacement occurs in the rotation about the y direction in this element, and the maximum forces occur here in element 15, just kind of a little bit underneath and to the side of the driver. And again, the fact that this element has the maximum forces and stresses just kind of indicates how important these cross members are, even though all the forces right now are downward forces and a little bit of x direction forces. This member is still pulling a lot of weight, so to speak. In case 2, it's the same case, but just at 120 miles per hour. And so as we would expect, we see the same things just magnified. And yeah, the maximum displacement increases, as does the maximum element force and element stress. But overall, same ideas. Case 3 is the turning motion, the car drifting through a left-hand turn. And what we see here is not too different from case 2, it surprised me a little bit. Flipping between them, there's not that much difference between the deflections. And you can see from the maximum values as well, the max displacement is fairly similar, a little bit increased. And the max force and stress are decreased in this one. And the car is moving a little slower at 90 miles per hour. And because we're at a slip angle, we're getting a significantly higher amount of side force, aerodynamic force pushing in the z direction. It seems to actually kind of balance the forces, the g forces that are throwing the chassis to the negative z direction. So that's just kind of interesting. They balance each other out well enough to where the effects aren't very well seen. Now, case 4 and 5 are the real tests of the chassis because, of course, the chassis it hopefully doesn't break during just normal driving, but it is at risk during a crash. And during a crash, we can see the downward forces were applied downwards at nodes 21 and 8. Can't see the 8 there, it's blocked by the 25, which is behind it. But regardless, the elements carrying the maximum force and stress is this element right here, which if we go back is actually just the same element that it's been the entire time, except now it's on the right side of the car instead of the left. So very interesting. That element seems to be extremely important. And it's connected to a lot of interesting places on the chassis. It's connected to this spot where the engine and the driver share a mounting point. And there's just a lot of connections in that area of the chassis going to the front of the car, to the back of the car, along the bottom of the car, and up to this vertical part going to the top of the car. It's really where all the parts of the car meet. The maximum element forces and stresses are pretty massive, as you would expect, but none of the elements yielded. They are all intact, and the driver remains safe in this scenario. Case 5 is including thermal strains from a supposed fire that weakens these elements. And what we can see here is the maximum force and stress. The maximum force and stress decrease, and the maximum displacement increases. And just looking at the shape of the chassis alone, in case 5, you can see the front and the rear parts of this truss do not bend inwards as much as they did on case 4. Notice how they bend inward in case 4? In case 5, they're more upright and closer to their original position. And what that indicates to me is that these weakened elements around the engine, because they're weakened, they're not as strong as they were in case 4, and they cannot pull these towards the center of the car anymore. I also made note of the stress in this element on each car, and it is, of course, a larger magnitude in case 5. I included some bonus load cases just to see what the template code could do, and just to have fun with the geometry of a sprint car. So the first one is case 4, but with 20 times the weight of the car exerted on those top nodes. And finally, the chassis does yield. You can actually see, though, from the actual displacement, the purple is the magnified with a factor of 10, but the blue one is the actual displacement. And to the naked eye, it doesn't seem that drastic. So this appears to be a very rigid structure. But yes, all the same patterns as before are just magnified, and we have a comically deformed chassis when we look at it through the magnification factor. Case 7 is a fun one with just 20 G's throwing you to the right and 20 G's throwing you backwards. And exactly what we would expect occurs. The weight of the engine, the driver, and the driver really throw nodes 4 and 17 outwards to the right. And the weight of the top wing really just throws the top out to the right. And we get this interesting twisting motion. And we can see just how stressed these cross members around the driver are, despite them not directly connecting to any of the forces. So, in conclusion, the chassis holds together in all the realistic scenarios. It's over-designed for safety, which is a very good thing. It's well protecting the driver. It does flex during normal driving scenarios. However, that's just deformation on the order of millimeters, nothing that's going to affect the balance of the race car. And third, cross members are not only important to enclose the driver, but also support the structure in unexpected ways. We saw that even though they don't, those nodes aren't directly connected to the forces, they have a lot to do with keeping the structure together and keeping it stiff.